real axis and your measuring axis both is your R multiplied with your cosine sine. So all the condition forms which are here are cosine theta, are sine theta, right? And another thing that now I think some of you are still confusing about the VIBO. Okay, what's the relationship between your VIBO and your so-called your time sequence mapping? Your so-called time sequence mapping here is what? As I mentioned at the very beginning, we have a transfer function. We have a transfer function. And what's the relationship between your signal and system? Your transfer function represents a system. And this one is a signal. So what's the relationship between your signal and system? How can you link between your signal and system? Is you can use a very important input. The input is impulse. So if in your continuous domain you implement the impulse to your transfer function, this is your output again. Similarly, in the digital domain, if you give a unique impulse, okay? You give a unique impulse, your transfer function will obtain the output as well. So, on the edge of your unit circle, where you got unit step, something like unit step keep a constant value, or something like a sine function, you always got a sine or cosine damping. This one to the unit impulse response. Your output signal can be described as a marginally stable case. But this marginally stable means if your input is a unit impulse. Unit impulse is what? You only got the input when your time at 0. The rest of the time, the input is 0. So at this case, your output is a constant value or is standing at a constant value. Right? But it's never 0. No. But what's the meaning for the VIBO? VIBO is for any bounded input. The meaning of the bounded input means if your input value is bounded by certain finite value all the time. For example, your unit step. Is it your unit step bounded? Yes. Because it will never be greater than 1. From time 0 go to the end. Your cosine sine always bounded. Your 2 times cosine sine also always bounded. Okay? Your epsilon of 0.5 multiplied with your cosine theta t is always bounded. Because all your input from all the time is a certain boundary, a certain finite value, you will never be greater than certain finite value. So for those cases, if you have an impulse input, you already have a marginally stable case. If I'm going to implement another type of bounded input, for example the unit step, for example cosine sine, then your output still will be bounded? Answer is no. And the correct thing to check your VIBO is not only to take your impulse response. If you take your impulse response, basically you're talking about this. But it's to talk about, to sum up all your infinitive types of impulse response. So you are not only give one impulse, you are continue to give impulse at each time. From time equal to 0 go to time equal to infinite. So if you implement your impulse one time, you already get some non-zero value. No matter it's a constant or it's standing as a sine or cosine value, which means you will never die out. If you have 1, you have a certain bound there, right? If I'm going to have 2, what do we mean? If I'm going to have an impulse 2 times, Then since this one is 1, I implement 2 times. I inflict 1 impulse, another impulse, I try equal to 1. What's the output? Instead of 1, output becomes 2. Instead of 1 sine, you get 2 sine. Instead of 1 cosine, you get 2 cosine. And if I'm going to implement infinity times, what you get? You get infinity 1 add up, infinity times, what you get? Infinity. I get infinity sine, I add up, what you get? I get infinity cosine, I add up, what you get? Infinity. So this is what I mean. It looks marginally stable in your time sequence diagram, but it means I guarantee you unstable in your VIVO stability. Because that's what it means when we have 1 times unit impulse, you already are marginally stable already. I'm going to give you another type of further input and push another further, you are jumped to the unstability side. Right? Alright? So from this I want to highlight one more time. Okay, for the VIVO checking, you need to take the impulse response, but not only your impulse response. It's an infinitive summation of your impulse response. Is alright? If your one-time impulse response is already marginally stable, then your infinity time summation of the unit part impulse will be unbounded. Why this is very important? Because I don't know what the exam question is there, but most likely if they are going to ask you to do some Z transfer function, give you a Z transfer function, ask you to evaluate the stability. Eventually what you get? Eventually you are going to evaluate where the post position. Right? So if the post position within the unit circle, you are very confident this one is stable. If it's outside the unit circle, you also very confident it's unstable. Right? But sometimes some people may confuse. If your pattern, your solution is on the edge of the unit circle, this stable, don't tell people it's marginally stable. When we talk about the stability of the linear system, we're talking about the boundary line. And all those at the edge is also unstable. Is it clear, everybody? Alright. So we need to move on. Okay, I believe this figure you have seen many times. So far, what we have described. We have described about this part for week 1. When we talk about how to digitize the series. Right? From here to here, this is how we digitize the signal. We have discretization, we have quantization. We also talk about this one. How to represent a digital controller, digital system by different situations. How can we solve the different situations? How can we convert the different situations by Z transform? And now what's next? Once we have a digital input, we have step function or difference equation, what do we get? We are going to obtain this digital output, right? We are going to get the digital output. After we get the digital output, what we are going to do? We are going to send the digital output as a control signal to our real physical. If you want to control the speed of the car, imagine what you are implementing. You are implementing a continuous control signal in the car. Right? So the car engine receives the response, you are going to change the power continuously. Right? You don't have any moment. You cannot say because my sampling time is, let me see, 1 second. That means every second I send a signal to the power engine, the power engine will start at that moment. After that moment, the rest of 1 second you keep as 0. You don't keep like the engine not like not like this, right? In between you will keep constant or a certain value, right? So your actual output from your control signal eventually will be a certain manipulating variable to change, to take an action, to take an effect on your fan. So the actual signal to your plan is a continuous signal. So now my question is, how can we convert a digital output into the analog output, which we are able to take action, which we are able to change the value we want to change. So this is something we are going to talk today. Okay? So after you calculate your output, your digital output, which is UK or UKT, is the digital output for your digital controller. Okay? So after you get a digital controller, usually the system will do is convert your digital to analog. Okay? So you have a digital to analog converter. Then you have a continuous output. Then this continuous output signal will take action and make effect your plan by the modeling of your plan, which usually we present as a function gx. Okay, now be careful. On this part, the digital part, on this part. So after you have a result, you take effect on your plan. You have your continuous input. Okay, pay attention. Small t. Small t is what? Continuous. Analog input. After you get the analog input, you may need to do the sampling again to convert to a digital input, which is here. Right? So you see we have a digital to analog converter from your digital input to your digital output to your analog or your continuous output. Then after you make the effect, take action, see the plan, then you are going to get your analog input to the system. But for the digital system, you are going to convert your analog input to your digital input. So you have a digital to analog and the output side, you have an analog to digital input side. And here is something we have learned before, is we are going to do some sampling. And here is something we are going to discuss today, which we are going to do some solving. So this is a traditional RC circuit, okay, for you to do the integration and so forth. And this is a typical home and the track system. So for example, if you have your digital input, for example, I have an digital input, I have one input here, I have one input here, I have one input here, input here, input here, input here. So how can we convert this one to a real input to the model? The model cannot say, I got some power at this moment, the rest all becomes zero. It won't be, right? So in between my current sample to my next sample, between my current control input to my next control input, I need to have certain weight. Okay? Of course, ideally, I'm able to track. So I have a smooth transaction. Okay? This is something what was. But we also have something easier or simpler to discuss in this moment. This is my very beginning continuous signal. So if I do the analog to digital converter, what I get? I get a digital signal is quantized, quantized, correct? But the digital signal is what? At this sampling time, I got value 2.3. But in between my current one and my next one, everything is 0. I don't have any signal, right? I don't have any signal at all. So one simplest way for us to convert a digital signal, we don't have anything in between. From one sample to the next sample, the most easy one is we do the zero order form. Zero order form is what? I just hold my current signal. And here I get main up. So if I receive current signal, for example, to be power for 40 watt. So I will on my engine for 40 watt. And here I receive the next input. If my next input is 50 watt, then I change my input to be 50 watt. Right? Then I keep as 50 watt. And here I receive next one. So this is the simplest way. We just hold zero order. I just hold my existing value and here I receive input. Alright? So if I implement the zero order form, I will get this one. Of course, this one has a certain distortion, right? But a perfect continuous signal. And in control, we use this block diagram to represent zero order form. Zero order. And we use something like a switch to represent the sampling system. So if let me say we have a continuous signal like this, after we have done the digital sampling, so this one we get this one. So this one is output, the R star, this one. Then if we implement the zero order hole, we eventually get this one. So this one is the outcome from your initial continuous form after sampling, after holding. Alright? And mathematically, what do we mean for sample? Mathematically, for sample, we will consider as multiplication with the in-out function, right? So at any sampling moment, we have an in-out function. Then this is the sampling means. So if I find 0, I have an in-out function, I took the sample. Because the rest, I need to fill out. At time equal to 1, I have another in-out. Then for the rest of the time, for the rest of the signal, and I sum up everything. Then I get all my digital. Okay? So basically, I say for time equal to 1 is when your impulse equal to first t. Then you get this signal, right? Then when your t equal to 2k, you get the second signal. And you combine everything together, you get this digital sampling. So digital sampling in mathematics is just the in-out operations, right? Just the in-out operations. Then how about the zero order hole? Zero order hole, first of all, zero order hole is not inhibition. First of all, zero order hole is not inhibition. Because you cannot do inhibition for digital sampling until hole. Hole means what? It means you are going to keep your value constant. If you keep your value constant, it's like you multiply with the unit step. Right? If I want to keep my unit, if I want to keep my signal constant, if I want to hold this one, it means I'm going to multiply with 1. If you're going to multiply with 1 means what? Means we are going for sample. I only hold for 1 sample time. That means I need to minus the rest. So you see this one, 1t minus 1 with a time t delay. This one means I'm only going to hold for 1 period. I'm only going to hold for t. Alright? Is all of you okay to understand this one? Yes or no? Yes, right? Because 1t means I'm going to hold this one. Actually, I'm only going to hold for 1 time period, right? Then how about the rest after 1 time delay? Minus all, right? So this is how you get the pulse. It's not in pulse, it's in 1 pulse. Right? So 1 pulse is your 1 unit step minus the unit step at 1. Okay? So if this is a time function, what do we need to do? We need to do the Laplace transform. Okay, why we need to do the Laplace transform? Why do we need to do the Laplace transform? There is a reason. So here I got my digital output. So my digital output we are going to have a zero order hole here, right? Your zero order hole, first of all, is it a continuous function? It's continuous, right? And later you get your output by your zero order hole, you are going to put into your plan here. Remember in your flow diagram, what you have done in the dynamics control? If you have one box here, what you are going to do is you want to multiply, right? Cascade, right? Cascade, right? So if you know the S function, you know the Laplace transform, this one, we want to know the S function. Yes, right? If I know the Laplace transform, this one, then later I can apply this to alright? Because at the moment we are not so interested in this. We are interested about here, how to get here. So you want to see we have a zero order hole here. Then we output of your zero will be cascaded to your plane. Then your plane will come out your action, your y key, right? Then this one later we are going to do the. So in order to continue, we need to do the Laplace transform of your zero order polynomial. So your zero order polynomial is, if you do the Laplace transform, this one, right? That one you can easily refer to your dynamics control or refer to your Laplace transform, right? So 1 is equal to, no, not equal, 1 can be converted to 1 to s. With any time delay, multiply with your delay factor, right? Your delay factor in your Laplace transform is e power minus, right? Okay, right? So now what you have to do, you have to use this one multiply with your GS and get this one. Okay? After you get this one, we are able to do we are able to find out the Laplace transform, the final one, and later we are able to get the handle of the one. Okay, so everybody okay for this one, right? Yes or no? Yes. So how is the Z transform of center of the inverse of y? So you have two parts. One is your zero order pole, the other is your GS. So this one is your zero order pole, and this one is your GS. And if you pay attention, you notice I put this one side, I put one and this side. So you can give another type of thinking. Just now I mentioned the zero order pole is not the integration. But actually what it really did the integration. Because you want to make it. Right? And you can consider this one as a certain delay. And this one can be considered as summation of two parts. Why this one, why this one? And if you have this one, you can consider this one as one time delay. If you do the Z transform. So if you consider that, the reason we can do that is because both Laplace and Z transform are linear. Okay, so you can do each part, do the conversion first, then you add up. Okay, then you add up. Okay, please be careful. The reason we get this one is not because we convert this one to be 1 minus 10. If we put this one into two parts, one is GS divided by S. GS divided by S. The other part is we look at this. And for this one is equivalent to a time delay. Because if we do a Z transform this part, and later we combine again. Okay, let me try that one more time. The conversion of this one basically is because we have because both Laplace transform and the Z transform are linear. Linear means what? The Z transform of this one minus the Z transform of this one is equivalent to the Z transform of the. So this one in total is equal to the Z transform of GS over S minus Z transform E power minus. This is where the linearity comes. Here at 2 you have learned this. property of the Laplace transform before, right? It's a linear, right? Linear means what? Linear means so you can do the individual transform first, then you sum up. It's equivalent to the summation of the two. Right? Okay. And be careful, don't be confused. You cannot apply A times B to the Z transform is equal to Z transform A multiplied with Z transform B. That one is not true. Be careful. That one actually most of other universities teachers can report. They are covering in detail. I don't know why. This last one they don't cover in detail on that. But anyway, since you are not going to detail, I'm not going to save your time. But you need to have a good understanding. Okay, your linear function is only applied for plus and minus. You cannot be AS. Okay, what do I mean is you cannot do this. You cannot see this one. You do the AS multiplied with your ES is equal to your Z transform of your AS multiplied with Z ES. This one is not true. Okay. But plus minus, yes. Plus minus. Okay. Multiplication is not true. Okay, so because of this, so you can do, because you also understand this one. This one itself is just one time delay. Okay? Of the GS over S. And this one you also got GS over S. So this is the reason is combined. Okay. And this one becomes a standard formula for you to handle the zero. It means you can just use your transfer function of your pen divided by S. Then multiply with, then you use this one, then you do the Z transform. And for that Z transform, now you are able to look at the table. Okay, why don't we can look at the table between the Z and S? If you remember, if you still remember, I highlight last week at the end. You cannot simple to map your S to your Z as a transfer function. This one is only meant for signal. This one only meant if you have this signal, then you will map to your S function in this way. If you have digital, if you do the discretization for your analog to your digital, you get this one. Then this one can map to your Z function. But now we are able to do the mapping because previously what you get, what exactly we are doing the mapping now? Now we are doing the mapping from here to here. Here I got my continuous input signal. Then I map, then I discretize it. I get digital input signal. Then I use the Z function to represent my digital signal. So now I'm dealing with, I'm not dealing with transfer function. So this one you must. Okay. So because of I'm dealing the signal, so now you should be able to solve this question. So So what should be the discrete transfer function of your GS processed by the zero order tools? So in order for you to first of all understand what the term is. So your math picture you should have your
Đúng sẽ.
and this one you mentioned that here you are supposed to get your
Đúng rồi.
here after you get the center. So now what we are talking about is frequency. So we are talking about we consider your UK as your input and your YK as your output, right? So basically we are talking about the YZ over the Z. Right? So this way you can consider as a Z transform between your YK and your UK. Sometimes we start the relationship. Okay, it's not properly written, it's not properly written. Because you cannot just simply use y case in the time domain. It's not properly written, but just want to let you know. We are talking about the transfer function between your y and your Alright? So now this one is talking about what? You're talking about your zero order mode, you're talking about your GS. So for this one, we understand the Z transform should be a zero order mode multiplied with your GS, because those are in the cascade in the time domain. So you have to do the Z transform of GS over S. Then after you have done this, you just multiply with 1 minus 1, right? So this one what you get? Your GS is A divided by plus B.
Good. That's the beer.
Then you multiply with another S. Get this one. So you have to do the inverse. Get the S. And don't forget to multiply with. And now we will refer to figure. And because this one is a second order, you may want to do a factorization. And factorization also is just a plus or minus. So it's a linear. And now you can look for the table. One side you have A divided by X. That one is simple. So is this one? So it's a conversion. Okay. The other one is S plus A. So you get this one. Basically is this one. Minus. So after your append the corresponding transform, okay, this one 1 over S, this one is 1 over S plus A. This one. After you get this one, you multiply with your 1 minus J power minus 1, which is this one. So you get this one. Okay, now, attention. Why I want to highlight, you are not supposed, you cannot just simply look for the table. Because some students will do is, okay, where is the S function, right? So we have the S and the A table, right? My function is what? My function is O A divided by S plus A, right? A is a constant. Some students may see, why not like this? If like this, what do you mean? Do you have a S plus A? Yes, right? If you did this transform, what you get? What do you get? If you do something like this, what do you get? 1 over 1 minus e power minus a e j minus c, right? Is it answer correct or not? It's not correct. Okay, this is the difference. They're not the same, right? Is it the same? Not the same. Why and not? This one never means transfer function conversion. This one can only mean equivalent signal conversion. So here, your x function basically is a conversion from your signal in the time domain. And here is the digital signal in the time domain converted to z. They are only meaningful. This one only meaningful when you are doing the signal comparison and is your continuous signal being sampled to a discrete signal. Why? First of all, from your analog, from the digital to the analog conversion, you have many. You can have zero order hole, you may also have first order hole, you may have second order hole, you can have many. So definitely there is no unique map between S and Z. The center is you're talking about the S function mapped to the Z function. Even if you're talking about the S function as a transfer function, what do you mean? Then your S operator is as a differentiation. Your 1 over S is as your integration. Yes or no? Yes, right. And what's the relationship? How you can convert or estimate or approximate the differentiation, the differentiation? You may have Euler's over, you may have Euler Weber, you may have time Euler. You got many ways to link between your differentiation to your difference equation. They are not unique map. Okay? 2 weeks later, we are going to learn some of the mapping between S and Z. But that one is based on certain assumption, which approximation you are using. Are you using the Tusky method? Are you using the Euler over backward method? And different method you are using, they are different answers. Don't confuse. Okay, we are going to learn something how to do the approximation from the S function to the Z function. And also we are going to discuss the difference in between. Okay, the error occurred due to the approximation. Okay, but that function level conversion, it depends on certain approximator to approximate the differentiation and this table is only means signal. It only means signal. Okay? Don't be confused. Don't be confused. You cannot just when it's title I got table. Then I can refer. You give me S function, I refer to the table, I find mapping and give you a Z function. And later I look at the table, you give me Z function, I give you an S function. It's not easy to work with such things. It's alright? Okay? So actually the process is not so difficult. The process for the zero order hole transfer functions conversion is not difficult. But you need to divide your GS over S. You need to divide your GS over S. Then you look at the table to do this type of. You only look at the table when you take the x. And not only that, you have to multiply with 1 minus 0 1. Okay? Because this one, they are going to do the mapping at the signal level. Okay? Your output, analog signal to your output. Sorry, your input out your input signal to your okay, the exercise for you to practice. Okay, we want you to try to convert a second order plan, very simple second order plan. Okay, and this one will be converted by 0. Any questions? If no question, we will end it today. For those if you want to submit your exercise answers, okay, to me to take a look and make a suggestions to us to go for the review next week. Okay, this has to be okay.